We have till now discussed linearization of inversion charge, that is a linear relationship between inversion charge and surface potential. We will continue with the same topic and where we will then derive a linear relationship between inversion charge and surface potential for strong inversion, weak inversion and moderate inversion regions. After that we will discuss linear relationship between depletion charge and surface potential. We have now obtained a relationship between the pinch off potential chi p and the inversion charge q I. So, that relationship is 2 q I plus natural logarithm of q I is normalized pinch off potential minus 2 phi f minus VSH minus V. So, how does this behave? Let us try to understand. Suppose the value of V is very small. What is V? V is the local channel potential. Now, chi p is a function of gate voltage. We had seen that. So, for any gate voltage, what is that value of surface potential where the inversion charge can be considered to be 0. In reality, the inversion charge would be 0 only if only for the flat band condition and also and it would never really be 0 for depletion. No matter how large the depletion region is, it would never be really 0. But in our linearized model that we have been discussing, when you extrapolate this slope, it would become 0 at some point, okay, and for any gate voltage here it becomes 0. So, that is because of our linearized model. So, as we had discussed in the previous lecture. So, it is never really 0, but in our model it becomes 0 and that we call the pinch off potential. So, where we can consider the inversion charge to be 0. So, that is for a given gate voltage, it is a unique value. Now, this local channel potential, what is this local channel potential? For example, in this case, because source voltage is 0, the local channel potential here is 0 and here the local channel potential is VDS. So, it increases from here from the source edge of the channel to the drain edge of the channel. So, that is this local channel potential V. So, this local channel potential, suppose it is 0. So, you have the highest value of 2 q I plus q I. What is q I? This is normalized inversion charge density and so it has a large value and it has a positive value in case when local channel potential is 0. So, suppose it has, so this is 0 and chi p is anyway larger than 2 phi f. 2 phi f is the value of surface potential when strong inversion takes place, approximate value. So, this has this left hand side has the largest value when V is 0. So, there it is the linear part 2 q I which dominates and natural logarithm of q I is, so suppose this is a large value then this is a natural logarithm of q I would be a much smaller value compared to q I. So, there be and so as the value of this local channel potential increases at a certain point, now this exceeds this and local channel potential is now larger. So, what would happen? This would right hand side would turn to be negative. What does that mean? It means that natural logarithm of q I is negative and larger than 2 q I. It means the value of q I, the value of inversion charge is quite small and therefore, its natural logarithm is a large negative value. Since the value of inversion charge is very small, its natural logarithm is a large negative value, large negative exponent it has and that is much larger than the absolute value of the normalized inversion charge. So, that is why for very large, for as you keep on increasing V, it could happen that this right hand side becomes negative and where the value of inversion charge density becomes smaller. So, as you keep on increasing V, we had seen in our previous lectures that the inversion charge density keeps on reducing and you also it would attain such a small value, the inversion charge density, that this is a large, it has a large negative exponent, and therefore, this dominates over this term, and that is how you find it to be negative. So, there is a value of this local channel potential where the left hand side becomes 0. There is a value of local channel potential V for which this becomes 0, is not it? So, what does that mean? 2 Qi plus natural logarithm of Qi is 0. So, what does that mean? That value of V, we call it pinch off potential, and that is the value of V for which that what is that value of pinch off potential? It is chi p, normalized chi p, pinch off potential minus 2 phi f minus V s h. Okay. So, now this is that value of pinch off potential. So, what happens when V is smaller than pinch off potential? Local, this V, small v, we call it local channel potential. So, this Vp we are calling pinch off potential. So, when the local channel potential, so what we can observe is that for a given voltage, this pinch off potential is defined, 2 phi f is defined for a given device, and VSH, as we had seen in the previous discussion, VSH is also defined for a given gate voltage and a given device. So, we have the pinch off potential Vp defined for a given gate voltage for a given device. So, now when the local channel potential is smaller than pinch off potential, so let us visualize this. So, you are increasing the local channel potential from 0 to VDS here. So, it keeps on changing. So, therefore, inversion charge keeps on reducing from the source edge to the drain edge. So, at some point you may have 2 Qi plus ln Qi, natural logarithm of Qi to be 0, maybe here. So, what is the local channel potential there? There we have a local channel potential equal to Vp, and for between the source edge of the channel, and that point where local channel potential is equal to Vp, between these two you satisfy the condition that local channel potential is smaller than Vp. So, what is happening there? There this left hand side is positive, means 2 Qi has a value which is larger than the exponent of Qi, okay, in magnitude, because exponent of Qi is negative. So, it is larger than the exponent of Qi in magnitude. So, in some sense you could say that the inversion charge is dominating, it is having a large value. And what happens when, so in this case dominates, inversion charge dominates. So, what happens when local channel potential is larger than Vp, pinch off potential? You could see that now this is negative, means the exponent of Qi is larger in magnitude than 2 Qi. So, it is as if the inversion charge density is smaller than a certain threshold. Okay. So, therefore, you would say that you can consider it to be weak inversion, that part, the part of channel where V is larger than Vp, there you can consider it to be weak inversion. It's, and the inversion charge density is much smaller. Okay. So, we could write this expression in a more simpler way, 2 Qi plus Qi, 2 Qi plus natural logarithm of Qi is Vp minus V. We could write it this way, the same expression. Now, we can use this expression in obtaining simple expression relating inversion charge and surface potential in moderate inversion and strong inversion. Before that, let us have a brief discussion on this VSH. We will see this through example problems, but as the value of Qi changes, what is the actual value of VSH? So, VSH we had derived it as natural logarithm of gamma b 2n by gamma b plus 2 times square root of chi p minus 2 qi. Now, here we had said that this is negligible compared to chi p in general, and because chi p is quite large compared to qi, again this is negligible, and that is how we had obtained the expression that this is actually natural logarithm of 4n by gamma b to square root of chi p. So, this can also be seen from here. As you keep on increasing Qi, for different values of body modulation gamma b, you would observe that VSH is almost constant, and that this holds for a wide range of values of chi p and gamma b. That is, chi p is again a function of gamma b. So, it holds for a wide range of values of gamma b as well as inversion charge. So, this approximation is justified, and we will see that through some example problems that we do as assignment. So, therefore, in the expression 2 qi plus natural logarithm of qi is equal to Vp minus V, our inherent assumption that this expression holds stands on another assumption that Vp is equal to chi p minus 2 phi f minus VSH is just a linear function of chi p. So, that is happening because VSH is almost constant. Now, we can rewrite this. So, when V is smaller than Vp, in that case you can approximate Qi as Vp minus V by 2. So, this is strong inversion. We will discuss this. And when V is larger than Vp, you can say that now Qi is exponential Vp minus V, and this is moderate inversion. Why is it so? When would this approximation hold, that Qi is approximately equal to Vp minus V by 2? When you can neglect natural logarithm of Qi. When could you neglect it? When Qi assumes a large value, large positive value. Positive anyway it is. So, in magnitude it is positive. So, and normalized inversion charge is always positive. So, this is a large value. In that case, natural logarithm of Qi would be much smaller compared to Qi. If it is say 10 to the power 12 per centimeter cube. So, this is 10 to the power 12 per centimeter cube, and this would be natural logarithm of 10 to the power 12. So, that is about 30. So, this is 10 to the power 12 and this is about 30. So, this dominates. So, whenever the normalized value of inversion charge crosses a certain threshold and this dominates, it is a large positive value, you can safely assume this to be negligible. So, there Qi is given by this function. So, it is a linear function with respect to local channel potential. So, the normalized inversion charge or inversion charge now changes or increases linearly as local channel potential reduces. Whereas, when this local channel potential is larger than Vp and suppose it is sufficiently large, you would find that the negative exponent of Qi becomes larger than Qi, 2 Qi. Now, 2 Qi is quite small. So, the negative exponent of Qi is large in magnitude compared to Qi. So, therefore, this dominates, this you can neglect, this term. So, in that case you would have Qi is exponential Vp minus V. Now, so this is so you have an exponential relationship now between the local channel potential and inversion charge. Okay. So, let us further see this. So, here you have Vp minus V is equal to 0. So, if it is Vp minus V is equal to 0, what do we mean by that? we mean to say that now this is equal to 2 qi plus natural logarithm of qi, now that is 0. So, on the left hand side of that, where v is smaller than Vp, qi we had seen would be Vp minus v by 2. So, that is this part of the plot. So, this region. So, here you have Vp, v smaller than Vp, and you have this strong inversion approximation being followed, and it is almost a linear function qi with respect to v. And the 2 qi plus wherever the value of v for which 2 qi plus qi ln qi natural logarithm of qi becomes 0 is a good separation between the two regions. And the other part of the plot, the plot below, for this plot we would again write it as qi is equal to exponential, that again you can see. Now, this is a, so here you have plotted it on a semi-log scale. So, this is y axis is, the y axis is plotted on a log scale. So, as you can see, so beyond this point where v is equal to Vp, when v is larger than Vp, you have a logarithmic relation or exponential relation. So, exponentially the inversion charge is falling, exponentially the inversion charge is falling here as the local channel potential increases. As you may have observed, these approximations are both valid for v being much smaller than Vp and v being much larger than Vp. So, these are valid in strong inversion and weak inversion, weak or moderate inversion. But when you are very close to the boundary of strong inversion and weak inversion or moderate inversion, that is you are in moderate inversion kind of regime, you would observe that neither of the two approximations are well valid. So, when v is comparable to Vp, neither of the two approximations are valid, and you must take this into consideration. So, we would say that this is for moderate inversion, strong inversion and weak inversion. Okay. Yeah. So, this expression is now very important. It gives us a way to quantify inversion charge with respect to local channel potential. Local channel potential is something which is known especially at these two edges. Here it is 0 and here it is VDS. So, local channel potential is in some sense a physically a parameter which can be related physically or intuitively to the values of terminal voltages that you have applied. Now, let us discuss the linearization of depletion charge. Till now we were discussing the linearization of inversion charge. Now, let us discuss depletion charge. So, what is depletion charge value? We had seen that depletion charge is gamma b square root of chi s into Cox. So, and it is a negative charge for n channel device. So, that this can now and what is the value of change in depletion charge with respect to the surface potential. So, that is equal to gamma b Cox by 2 square root of chi s, isn't? Now, what is this? So, we already know that the value of the slope factor is given by this. So, this is therefore, this is 1 minus n Cox into 1 minus n, and therefore, you get that 2 dqb by T Cox is dqb by Cox, qb by Cox, the derivative of qb by Cox with respect to surface potential is 1 minus n. Now, what implication does it have? We will discuss that. So, here you are, as you are going from the source edge to the drain edge, the depletion charge is keeping on increasing for a non-zero drain voltage, positive drain voltage. Now, let us define term QBP, which is the value of depletion charge for chi p, that is pinch off potential. So, that is given by this expression. So, now if we linearize the depletion charge value with respect to surface potential, what would we get? So, what is the value of change in QB with respect to a change in surface potential? So, that would be Cox into 1 minus n into delta chi s, change in surface potential. So, what is the implication of this? So, the value of depletion charge for a given value of surface potential which is smaller than pinch off potential chi p would be the value of inversion charge at pinch off potential chi p plus 1 minus n into delta chi, change in surface potential. Now, you have changed it from pinch off surface potential to chi s. Now, chi s is smaller than chi p. So, this is negative, n is larger than 1. So, this is also negative. So, this is a positive quantity. This overall is a positive quantity. What do you mean? You mean to say that this is negative, this is positive. So, for any other value of chi s which is smaller than chi p, you would have a smaller depletion charge. The magnitude of magnitude of depletion charge is smaller. It has a negative, it is a negative charge. So, QBP is given by this and the change in QB for the surface potential is given by this. Now, this is a linearized function of QB. So, how do we normalize it now? So, let us normalize it as a normalized depletion charge. Let us define it as QB by Q specific. Q specific we already know. So, what would be its value? So, let us derive that. Now, it has two parts. QB by Q specific is minus gamma b Cox square root of chi p square root of normalized chi p or absolute chi p. So, here it is absolute chi p square root of chi p divided by minus 2 n Cox ut. This is the value of Q specific plus 1 minus n into chi s minus chi p Cox divided by minus 2 n Cox ut. Now, this is the value of normalized depletion charge. Let us look at the first term minus gamma b Cox square root of chi p divided by minus 2 n Cox square root of ut square root of ut. So, if you write it this way, now it is minus gamma b by square root of ut into gamma b square root of normalized chi p by 2 n. Likewise, you have the other expression. So, you can write the second term, this term as 1 minus n by n into n Cox chi s minus chi p by minus 2 n Cox ut. So, what is this? So, this is n minus 1 by n into what is n Cox chi s minus chi p? As we had seen earlier, it is actually qi by Cox. N minus 1 by n into qi normalized qi. So, this so, therefore, we have now obtained a linear relationship in normalized terms, all the charges obtained seen in normalized terms with respect to which relate the depletion charge and surface potential. So, how do these expressions look like? The inversion charge is this. So, normal and depletion charge when normalized is gamma b square root of normalized chi p by 2 n plus minus n minus 1 by n normalized qi. Okay. And let us now also see this interesting thing, how do you obtain the value of depletion charge from this plot. Yeah. So, this is we had seen that dqb by Cox by d chi s, this is not normalized surface potential, it is the absolute surface potential, not normalized. This we had seen to be 1 minus n equal to 1 minus n. Okay. So, what is the value of depletion charge for chi s being 0, flat band condition, that is here it is 0 ideally. So, though linearity is not valid here, but we can, if we extend the ideal straight line to the origin, we should theoretically see it to be 0. So therefore, QB can be written as 1 minus n QB by Cox can be written as 1 minus n chi s. So that is what you have done here. So therefore, if for a given Vg, if this gives the absolute value, this difference gives the absolute value of Qi by Cox, this difference gives the absolute value of QB by Cox. Okay. So, this part of the y axis gives the absolute value of QB by Cox, this part of the y axis gives the absolute value of Qi by Cox. So, today we have discussed a linearized expression of inversion charge and surface potential. We have seen in strong inversion approximation and weak inversion approximation, and we have also seen the expression which relates the inversion charge and local channel potential in moderate inversion. We have also seen the linearized depletion charge expression and how the depletion charge relates to the surface potential and a normalized version of that expression. Thank you.